in. So thank you everyone for bearing with us. To go ahead and kick things off, you are tuned in to yet another HackerVillage episode, and this time it's ETL, baby. So y'all remember the good old days of Jersey Shore? GTL? Well, this is ETL. I am Catherine Mills. I am the host of the Crude Audacity and an operations engineer at Surtek. My co-founder on my computer screen, he's right below me, is Mr. Matt Bauer. How are you doing tonight, Matt?
Good, good. I'm excited for this one. This is going to be a lot of fun.
This is going to be so exciting. So before we turn it over to tonight's instructor, let me give a huge shout out because as you know, it takes a village, as Matt and I were talking about earlier. So if it weren't for our advisors and our sponsors, we would not be here tonight. So first and foremost, huge shout out to Josh Cherlick at Well Data Labs, followed up by Ms. Sarah Derdowski at the GEM program. Seriously, if you were looking for a future in energy, the GEM program is where it is at. And then Mr. Jim Thorson of Free Radical Ventures. We ran all of these ideas by them in the very beginning, and they helped us formulate a plan to bring open source, collaborative, hands-on Python coding to the oil and energy sectors in the form of HackerVillage. And of course, last but not least, Miss Terry Olson. Y'all, she is heading up the Members in Transition group over at RMAG. And I swear, this group genuinely cares about the future of oil and energy. They had no reason to reach out to us, yet they saw what we were doing. And because of them, Matt and I are able to continue this through the end of the year and into next year. So if you are not a member of RMAG, I suggest you look them up and look for their links in the show notes below after this because, again, they are an organization that truly cares about the future of energy. So, huge other shout out. This is not one of our sponsors, but as I said, I am an operations engineer at Surtek, and tonight's instructor, Mr. Elii Skeans, is the reservoir engineer over at Surtek. And that is our group where we have been doing enhanced oil recovery since really 1978. We have more implemented projects than anyone else in the entire world, which is pretty damn cool. And just filling in some blanks there, enhanced oil recovery is a part of field development. So if you are curious, please feel free to bombard Eli with any and all questions because he is one of the designers of the global EOR database that Surtek offers. So without further ado, Matt, did I hit everything?
I believe so, Catherine.
Eli, thank you so much for joining tonight for ETL, man.
You're welcome.
Tell us all about yourself. How did you start in oil and energy? Why coding? And how did I volunteer you to join tonight?
Yeah, no worries. I'll give a brief introduction here. So, name's Elii Skeans. Like Catherine said, I'm a reservoir engineer at Surtek. I graduated from the University of Akron with a bachelor's of business, focused in international business back in 2013. I moved to Denver shortly after that looking for work. I found some work and it wasn't too satisfying, so I decided to go back to school where I went to School of Mines and graduated from there with a bachelor's of science in petroleum engineering. From there, I started work at Surtek, and since then, I've started a master's degree in data analytics, which I'm about 30 days from completing. So, looking forward to that.
Congratulations on that.
Yeah.
Well,
so at Surtek, I do numerical modeling mostly for enhanced oil recovery. So compositional modeling and CFG products like STARS, IMEX, and GEM. Also some experience in Eclipse, and had the chance to work on projects in South America, Africa, and the Middle East. So it's been a great learning experience.
That's fabulous. Well, Eli, before I say the famous words, does everyone have a beer or a glass of wine? Awesome.
I've got it, I swear.
Well, on that note, tell us about ETL because everyone, it's time to grab a beer. Let's code.
Yeah. So I was going to give a little spiel on Surtek, but I think
Oh, go
Catherine,
for that too.
Well,
They'll love it.
you covered it pretty well. But yeah, so we specialize in enhanced oil recovery. That's anything from chemical to gas injection or steam or any forms of liquid IOR even. Really comes down to field development, and we're experts in modeling those cases and also doing laboratory studies to design the best techniques for your asset. And we've done that all over the world since 1978. So my role as a reservoir engineer, and especially at Surtek, we're dealing with these projects all over the world. And it's pretty quick turnaround compared to other people's workflow. So I have the pleasure of dealing with very large, unorganized data sets often, which is the origin story of my Python experience. So during School of Mines, near the end, I got cued into Python and the advantages that could have in handling large data sets, which are inherent in oil and gas industry. As we all know, there's production data can be millions of lines long, or you have seismic data, which is a whole nother monster. There's just all kinds of data sets that you can run into. Each of those have their own challenges, and they also have many different formats that they come in. Production data that I've seen from fields all around the world, every project I've worked on, it's come in a different format. So when I need to analyze that, or my boss wants some sort of plot or analysis done, I've got to wrangle that data and figure out how I'm going to get it done. So Python, I found, is the best tool. Pretty much self-taught in that. The resources to teach yourself are all there online. And I would say you could get pretty comfortable in Python in a couple months of dedicated practice, at least to get to a point where you can apply it in your own work. So I'll jump into the presentation here. In addition to Surtek, I've helped Elii to proctor some classes at School of Mines in the Petroleum Department, specifically data analytics and oilfield economics. The data analytics course, I wrote a few of the modules, or all the modules that use Python and Spotfire, since those are my strong suits. Spotfire is a dashboarding program, which we won't cover here, but if you've taken the data analytics class, then you might be familiar with the first segment of this presentation, which is how to wrangle the Wyoming Oil and Gas Commission field data. So
Wyoming's field data, the downloads are terrible.
It's horrible.
That's absolutely horrible. I hope someone from the YOGCC is listening, because what the literal hell.
At least they're there all in one bulk download though.
That is awesome. That part is
There's
awesome.
other states that don't have that. So
that's true.
Which states, Matt? You want to call them out?
no.
Nebraska. I'll do it. I had to write a web scraping thing to get field data for Nebraska, and even then it was inadequate because it's by lease instead of by well. But that's just another example. So what Catherine's referencing is that the data on the Wyoming Oil and Gas Commission website in the United States, all the oil production data is made public. So the state website lists that data, and every state does it. The format that they list it is different, and some are easier than others. So the problem statement, I guess, for this is, let's say you want to analyze a field in Wyoming, and I just picked a random field out of a hat called Hartsog Draw. The reason I chose it is just because it's got a lot of wells, and it was the first one I sort of stumbled upon. So no real rhyme or reason there. So how would you get this data, I guess, is the starting point. A lot of people that work at companies, they have some sort of commercial software subscription service that they pay for. That might be Drilling Info. That would be the easiest place to get the data. But if you're an independent guy, let's say you're trying to buy an oil field, or you work for a small company that would much rather not pay for these services or don't have the budget to, especially during COVID. How do you get around this? So I'll show how you can get the data off the Wyoming Oil and Gas Commission website, download it, and then show you how a transform is needed in order to use the data. So this is can you see this, the Wyoming Oil and Gas Commission website?
Yeah,
so
we see it.
This is their glorious website. You see this tab for data here. You can click that and you'll get, they'll tell you all the data that they have available. One of the data options is for field data, which is what you see here. So you get this box. Now you have to scroll down and find your field, right? And then you can select that field and you can choose download production by well. You'll see that here, and what you'll get is this. This is a list of every well in that field. Spoiler alert, there's 380 something odd wells there. So to download the production for these, you have to check each box. And then when you're done checking each box, just praying to God that you don't miss one, then you hit submit query, and then you would get a download. I think I'm not alone in saying that nobody wants to scroll through 380 odd wells and check 380 boxes because that's horrifically mind-numbing. So you want to avoid that. So the other option is you can go to a download menu where they have these two options at the bottom here. This is production data from 1978 until the present day. So September of 2020 is the last time the production was reported. And the wellheader data is also needed. You'll notice when you download the production data, all that you get is API numbers with the raw production data. So if you're looking to match those API numbers to a field, you need the wellheader data as well, right? So you got to download both of those. What you get when you download those are zipped files. I guess I can show you that. So the production data comes, when you unzip it, you get these 4 Excel workbooks, and the well headers come in these .dbf files, which you can dig around online and figure out that you can actually open those in Excel, but you can open them with Python as well. So jump back into this. So now you want to load this data, right? We have all the production data from the state, and we have the wellheader data, so we know that we can query the wellheader data for a field of interest and match that to the production data. That's the general workflow that you would be approaching this with. So this code I've written here, I'm not going to run it because those production files take about 25 minutes to parse using this module. Matt cued me in on some methods to maybe make that quicker, but he's a lot smarter than me, so I wasn't able to apply that.
I don't know about that.
Well, you got cooler shirts than me, at least.
He loves his Hawaiian shirts. It's a geologist thing, I swear.
It goes well with the snow that we've got here. Yeah, so this module, this is a good thing to know. I'll just, before I get into the code here, I'll just premise this with, this is absolutely not the best way to do any of this. It's a way to get it done, and the goal of it is to just expose everyone where, you know, if you're new to Python or you're getting intermediate level Python, some of these things you don't know until you see someone else try it. So for example, this glob package is super useful when you have a bunch of files in a folder. So in our case, we have 4 files. I could manually load each one. That's manageable to do with only 4 files. But let's say you have 100 production files and you want to aggregate all of them together. You can use this glob module to cycle through every file in that folder. So I've got a folder. My productions data is stored in a folder called YO. And each of these files starts with the word counties. So I say, go to the folder YO. Any file that starts with counties, that's what I'm interested in. So then down here, first I initialize an empty data frame that I'm going to aggregate everything into. And then I use the glob module and I say glob.glob, follow my file path. And I tell pandas to read that file. So in that for loop, it reads the file, and then I concatenate that data frame into my empty one. It starts out empty, and then as it loops through each of these files, it concatenates each one together until finally you have a file. I printed the shape of it here. So this is 1.5 million lines long with 54 columns. Anyone who's broken Excel before, you'll know that this will do that. So what do you know the row count limit, Matt, in Excel?
It's like
I don't
10,
know right off.
10 something. I just all remember.
100,000, that might be right. Anyways, just to break it, if you open one of these files in Excel, you'll find that it spins for a while, and you wonder if you need to restart your computer, and then 10 minutes later it'll give you a warning message that says that it's only partially loaded. So that makes this problem the perfect example for Python, in my opinion, because you literally can't do this in Excel. So you don't have the option. If your boss said, here's these files, figure this out for me, you would panic a little bit and not know what to do if you didn't know Python. So that's how we load it all into a single data frame. This is what the data looks like. So this is the head of that file. You can see we have the API number. Like I said, there's no other identifying information like the field name. You have a column for year. Then you have a column. This is the annoying part, and it also highlights the need for Python here. So you have January oil, January gas, January water, January days, February oil, so on and so forth until December. And I challenge anyone out there to try and plot this data on a simple scatter plot, because you won't be able to. If I said plot the production from one well, you wouldn't be able to do it. You'd painfully try to grab it manually and then reorganize the columns and maybe make a mistake and really put yourself at risk of looking like a jerk. So before we get into the transform, the other missing part, or the part that's needed, is the well header data. So this is the head of that file. All I've done is read that in pretty simply. That's easy to do. And you can see you have your API number, company names, and we have field name here. Okay, so I know the field, I found a field that I'm interested in. Like I said, it's Hartzog draw. And we'll query this data set for that, only those API numbers which are in that field. And then I'll pare down this data set to only include those API numbers. Okay, so that's the way I chose to do that. So I do that here. So because the first bit of code takes so long to call in, what I'd done is I did the query already. So I query the well header data for only Hartzog draw, and I say I only want the API number. Now I go to this is the data set that I conglomerated all the state's production into, and I say that I only want the part of the data frame that has where the API number is in the list I created here. So this function .isIn is really useful for querying a list of values from a data frame in Pandas. And then here I just created a cheater file so I could avoid loading the initial data set during this presentation. So now we'll jump into the transform. We'll take a quick look at this again. So this is the data we're trying to transform. Okay, you can hopefully imagine how this would need to be. So for 1978, I want, January, I want continuous time series data is what I would call it, right? So January, February, March, April, May, June. And I want a column for oil, a column for gas, and a column for water. And maybe a column for days if you're interested in analyzing that. Okay, so so we've got that data loaded in here. And in the star of this transformation, for me, the tool that I chose to use is a function that's built into Pandas. So I highlighted it here. It's called melt. And it's the perfect tool. It's the only tool I know of really that does this really well. So what I'm doing here is I'm telling it a few things. First, I'm telling it the variables that I want to keep around. So the API number and the year, keeping those. I'm also building a dictionary for the columns that I'm going to query. So if we go back up here, we have January oil, January gas, January water, and we have that for each month. So each of oil, gas, and water are 3 variables I want to capture, right? So I cycle through oil, gas, and water, and I build a dictionary for each one it's going to make a list here that says January oil, February oil, and then once it's done with oil, it'll say February gas, March gas, and so on. And then I'm going to create.
Eli, may I ask a question?
Yeah, absolutely.
So you are using the variables there, and you have the %, an underscore %, and S on the end of them. Is that why is that happening?
Okay, great question.
That inserts.
Yeah, so I don't know the exact lingo for this, Matt, if you do, but really it's this is a Python function. This isn't specific to pandas or anything. So when you're creating, let's say you have a variable that you want to insert into a sentence or a string, that's what you use this for. So %S says that this string is going to say value, theirs, underscore, and then whatever variable I put after. So after my string, I put another %, and I put my variable. My variable is X, right? So I'm cycling through this list. So at the first iteration, X equals 0, oil, which is a string, right? So what it's going to do here is it's going to name this dictionary or this list value, bears, or oil, and each one of these components will be named. The %S will be replaced with oil. So January oil, February oil.
Oh, that makes a lot of sense. Thank you.
Thank you. Yeah. So what we're doing here, because the reason I'm doing that is because I have to tell Melt which variables I want to grab and turn into rows. So I have column values that get transformed and drop down into rows. So I say, when I pass this list into this here, this is where the list is going in. I'm saying, grab January oil and February oil and so on, and put those down as a row item. And it's going to make a new column name because the new row has to have a column name that can associate it. I'm going to call that the month value. And it's going to say January oil in it for now until I clean that up later. But that's essentially what's happening. So it creates a column called month val. Each row for this first transformation is going to say January oil, and it's going to drop January oil down as a row, and they're all going to have the same year. So that's the first transformation. We need that 3 times for each of these variables. So then the result is this. So, there's some cleaning that's done here. This is just legwork, right? So, like I said, it renames the column January oil. So I created a dictionary that turns the word Jan, Jan, into 1, which is the numeric value for the month of January, so on and so forth, till eventually I map that column to be a date rather than just a useless January oil. So this stuff is nothing special. I use regex in here, which, you know, that's a whole nother beast in itself that can have a whole nother lesson. I think Matt is good at that sort of stuff.
I always have to look up the syntax, but man, regular expressions, they can give you superpowers.
Yeah, so that really is the star of natural language processing, which isn't really in the realm of a petroleum engineer, but that's really a big part of data analytics in general. So these tools you can check out this stuff. It's sort of boring cleaning, right? To get the Matt says no, it's not boring.
No, what's boring is doing it by hand.
Yeah. All right. Great point. Yeah. So this code, there's always this battle for me and for everyone, I'm sure, and this should be a consideration. You don't want to. Sometimes I get excited by Python, and you get sucked into this hole where you start coding something that you could have done quicker manually.
Like find your car on Craigslist.
Yeah. Hey now.
No, that one's great. I've got a medium.com article about that. I can share a link. But
heck yeah, share the link. I'll put it in the show notes.
But Matt has a good point that what really sucks is someone says that you have to get this done. This is your job, and you're faced with doing it manually or writing code. And I guarantee you writing code is more exciting, if not, hopefully, way faster and reusable.
Yeah, that's the key thing. You can reuse it because you may be able to do it once faster, but if you have to do it more than that, take the time, write it up, set it up on a scheduled task, and then don't ever touch it again.
Yeah, and write it well. Comments will save your life. Mm-hmm. Something that seems so like unimportant in the moment. A month later, when you have to revisit your code, you save yourself an hour just by writing a comment to yourself.
Or you pass it off to somebody else and they have to do it.
Exactly. Yeah. Yeah. So,
Catherine.
So, I mean, I've already explained this here. I'm basically transforming I should have shown the intermediate step before this, but essentially you're transforming, creating a dictionary that you can then map to, that's what I'm doing here, mapping my month transform dictionary to my month val column, turning it into, so then what I had after this step, what you have is a column that's called year. Then you have a column called month val. So that's the numeric for the month. And then you have your oil, gas, and water. So what I wanted is a date time column. That's what date is here. So in order to do that, I'm using PD. So this is pandas to date time. This is another very useful thing. Sometimes you'll read data and you'll have a date column, but pandas or Python's not recognizing those values as a date. So you might need to use either to date time or the date time package itself to transform values into an actual date time. Otherwise, you'll have issues with plotting and stuff. So, I was passing I just created this mathematic equation to create the date. You can pass in just a hard integer for a date, and the years are 10,000s, and the months are hundreds, and the days are single digits. So you can create an equation to do that. There's
I never knew that. I always just pass the string in.
Yeah, you can. So the problem is that if the string isn't, the to date time package is pretty good at recognizing multiple string formats, but sometimes it goes bust. So I think it must have gone bust here, and I decided to write this equation.
The more you know.
Another great point is that there's like we say here in the U.S. I know we got a bunch of international viewers right now, but many ways to skin a cat. That's quite grotesque saying, but What essentially there's 1,000 different ways to do what I'm showing you, and
It's not that grotesque.
Yeah, I'm sure Catherine's got some more grotesque versions. But yeah, so I don't really look for I'm not sucked into trying to find the best, most elegant way to do things. Usually I just try and try again until something does work, and that's something, once it works, I move on. I don't look for the most elegant answer, which, shame on me, but sometimes you just got to get the job done. So that's really where I come from, is just, how do you get this done? How can we just get to the answer? So after I do those transformations, I have leftover columns that I don't care about anymore. So I drop these, the month, val, and the year, print the head of what we got. And now this is something that, we're all familiar with, and we could plot easily and work with and analyze. The dates seem to be out of order, but that's easily fixed. So now we've gone from this annoying, completely unusable format that you can't even open in Excel, to this clean transform format that only contains field data from the wells in our field of interest. So now you want to do some decline curve analysis. If you're watching this video, surely you know what ARP's equation is. So if not, maybe you're still in school at School of Mines or somewhere else, but ARP's equation essentially is created in the 50s, and it's used in asset valuation. So physics are implied or built into this equation to capture the normal decline you see from conventional or even unconventional assets. It's really arguably more applicable to conventional assets, which is where pretty much 90% of my work life lives in conventional assets. So for decline curve analysis, what you do is you grab the production from a well and you apply a decline to the most recent steady state flow that you have in the well. So you might have some build-up period or previous completions, and then you have some recompletion a couple years ago, and that's what you grab and base your decline off of. So that's what I do here. So the two packages that I focus in to get this done, there's two parts to it. There's fitting the curve, so that's math, right? So you need some math functions for that, and then there's looking at what you're doing, because spitting out numbers on your screen, unless you're some sort of robot, it usually doesn't do much for you. So building a visualization that you can look at and see how well your fit is, for example, or if it's also a great way to see if you just totally screwed up. So I choose to use Plotly for that. So there's tons of visualization packages: Matplotlib, Bokeh, ggplot, that's R, I guess. There's a bunch of them. So Plotly is one that I like because it can make quick interactive graphs, which we'll get to see here. SciPy comes native to your Python downloads. So it's an environment within Python that essentially has built-in math operations. So things like integration or optimization, which is the function we'll use. Those are built into SciPy, so that you don't have to code from ground zero how to integrate across the equation.
Lots of signal processing stuff too.
Yeah, that's for people nerdier than me. So specifically, you're going to see me using Plotly Express, and Plotly Express is great. It's amazingly easy. You can, with one line of code, you can make an interactive graph that you can click, zoom, highlight, filter. It saves you a ton of time. This sort of thing is built off of Matplotlib, which is sort of one of the founding members of the Python graphing capabilities. So let's jump into it. So I've imported Plotly as PX. That's the standard that you'll see. I chose a random well in our field. So I looked at the list and I grabbed an API number that was still in production so that we could grab a decline off of this well and try to see how much life it has left in it, right? You'll also see some graphs for using Plotly graph objects. It's just another package within Python. I use that to make a map that we'll see here down a little bit lower. So, like I said, this first bit of code is making a map. So I do some work on creating a color scheme for my map. So let me just show you the map first. This will ease things up a bit. So I've got a map of the field here. It's interactive. I scroll around. I see the API number below the coordinates. I didn't name the traces. I could have named them something special or magical, but this is what we got. So that just to show the vision that I had of what I wanted to create before doing this. So I wanted to have the producers as green dots because they make oil, and this field is doing this is actually an EOR field. I believe they're injecting CO2. So these aquamarine or light blue dots are the injectors, right? So they're on about a 10-acre spacing with some line drive patterns in the field. So all the way up here with our wellhead data, buried in here, there's a column called well class, and that is the column that tells you if it's an injector, producer. MW stands for monitor well, or D is disposal. So the monitor wells I don't care about. I just said make those black. Disposal, I'll just call that an injector. So injectors and disposals are going to be light blue and oil is green. So what I did is I'm creating, this is a pre-existing data frame. This is the data frame that holds the wellhead information. I'm creating a new column called class color. And what I do is I say class color, this new column I'm creating, is equal to this well class column, but map this dictionary. So essentially open the well class column. Anytime you see an I, change it to cyan, or anytime there's a no, change it to green. And these numbers, or these colors rather, I know are standard colors in Plotly. So I can pass this directly into Plotly and it'll know what cyan means, it knows what green means, it knows black. So now I have a column that has a color for each well. I subset my data further. This is to get secondary trace for just my well of interest, because you'll see the well that I've isolated, I've made a red dot just so you could see where it is in the field. So if you were actually using this for a workflow for doing decline on a bunch of wells, you could cycle through these, or maybe you're interested or you have the opportunity to just buy these wells down here, so you isolate these and do declines for those. It's just good practice, I think. Anything oil field, there's a spatial component to it, so understanding your reservoir and where wells are spatially is good to do. So you can do that easily with a map. I added this in later, which sort of busted my original 30-line code, but I figured better bells and whistles than make it too short and sweet. So in addition to where this well is in the field, we want to see its production data, right? So there's the production data. To get this done was this one line. So this is the Plotly Express magic that still blows my mind to this day. So I tell it the data frame that I'm interested in. and the column that represents X and the column that represents Y, and boom, I have this map that's completely interactive. I can see it's only plotting oil right now, but I can see, I've got a tooltip for each of the points. I can zoom in, I can go back, I can do a bunch of stuff. I can also deselect points and have that tied to some analysis as well, but we won't be doing that here. So we see this production data. It's pretty messy. We see an initial decline here. There's some sort of activity that happened here, and then we've got something here, the most recent, probably a recompletion or something, or some sort of acid
pump jacks. They changed pump jacks.
There you go. That could be it too. So really, we want to decline off this curve. That's what I would say is best practice, right? So first thing we would need to do is subset that data. So I'm looking at this point, May 2017, right? So I want to just look at the data after May 2017. So I created a variable here, named it arbitrarily, and set it for the month prior to that. So then I subset my pre-existing production data set. I say, I've got two things that I want to consider. Okay, when this well, first of all, the Oil and Gas Commission, for some reason, gave me months after, like I have December 2020. That's in the future, so it's listed as 0. I don't want, if I include these points, my decline is going to be jacked down artificially, right? So there's two things that I try to do. I want to say I only want production data before this date, right? So greater than this date. And I want only production data where the rate wasn't 0. Because also you can have times like this. This is before our date range, so it's irrelevant, but you might have this here where they had to shut in the well for some reason. That's not reflective of its performance or its inflow potential. So you would want to eliminate those points in pretty much every decline that you would try to fit. So this is a useful thing that's not super obvious. Pandas, you've seen me do a ton of times up above, subsetting a data frame with just one of these requests, I guess, or queries.
It's a Boolean filter.
Yeah, exactly. So if you want to do two things, so if you have like this and that needs fulfilled in order for you to create your subset, you put them in parentheses and you separate them by an ampersand. So that's how you do that. I didn't know that for a long time, so I would have had this as 2 lines of code, which
still works.
Still works, like exactly. So that's been my evolution. Is I started out writing just horrible code that if I open now, I'd just be so ashamed. And you eventually you just keep picking up tricks until you don't need to look stuff up anymore, and it comes naturally, and you usually have 90% success. So we got this data. I went ahead and plotted the subset that I have. This is after eliminating the prior stuff and eliminating the zeros. This is what we have. You could argue that maybe we decline this instead, but we'll just go with what I've got, which is from here to there. So the goal here, I've positioned this as being like you want to value this well. So you want to fit a decline to these points, and then you want to project that to some economic limit, which is whatever limit you think you can operate this well at. Once you start taking a loss from operating the well, you'd shut that in. Maybe that's 5 barrels a day. Maybe it's 3. Maybe it's 10. Everyone's different and every field's different. So I just made up a number for this case. But before you do that, you need to create a function. So Art's equation, there's 3 possibilities with Art's equation. There's harmonic, hyperbolic, or exponential. So hyperbolic is when the b variable is between 0 and 1. Exponential is when it's 0. and harmonics when it's equal to 1. So due to the nature of the equation, if you try to pass a 0 in here, you're going to get an error because you can't divide it by 0, right? So there's people that have already done the legwork for you to reformat this equation into the various forms for harmonic, exponential, or hyperbolic. Sorry, this is hyperbolic. So if you've never created a function in Python, that's a useful tool. If there's something that you're doing, some calculation you're doing over and over again, you can create this function. So then in the future, I can just pass the function, and you can see the variables I have here, T, QI, B, and D. So T is the normalized month or year value, depending on the format of your data. Q is the initial flow rate. B is your B factor. It's just a unitless component of ARP's equation. D is your decline rate. We're looking at monthly data in this scenario, so that's 1 over a month is the unit for that. It can be 1 over a year if you have yearly data. But you create a function here, so I've created some elif statements based on the value of B, and put in something here to prevent it from going over 1 because I'm not interested in that happening. And now our function is created and ready to be used later in our code to fit things. So we want to fit this data. We have it subset into a data frame I call DCA PRD sub. Okay. So first thing I do is, this is just cleaning. So I just sort the data frame and reset the index. When I reset the index after sorting, you get, for the first month is 0, the second one is 2, the third one's 3, so on and so forth. And that I use as my normalized month data. If you've ever done decline curve analysis, you know you need T. You can't pass a date to the T variable. You need a number, right? So you're starting, I'm doing this in months, so I'm starting at month 0. Month 0 equates to this point. And yeah, so I'm setting up my optimization function. So I need X data and Y data. So I just tell it, just like I explained, the index is my X data. The oil rates are my Y data. This is P sub 0. This is, I just named the variable the name of the component of the curve fit equation. So in this curve fit equation, you have the function that you want to optimize, DCA, right? That's what I called my function. You have your X data, your Y data, and then P0. P0 is your initial guess. So in my equation, I have 4 variables, right? So I need to pass an initial guess for those variables. I'm sorry, I have 3. So QI is the target variable. I mean, not QI. Q, your rate, is your target variable. So T is not a variable that you input directly. Anyways, you put in your initial guess for those points. So for B, I put 0.5, and for the decline, I use 10%. Okay. So that's just a starting point. It needs, just like with goal seek in Excel, you need some sort of initial point. So the curve fit function takes those arguments, you run it, and you get 2 arrays from that function. You get the fit for your variables, that's in this POPT array, and then you get a covariance array. I'm not too interested in the covariance array. I just want to see what predicted variables it chose. So I print those out here. I print out the initial rate that it chose and the B factor and the D factor. So what I've got is initial rate of 1217. That seems reasonable compared to this initial rate of 1261. B factor of 1 and a decline of just under 10%. So it doesn't seem like it broke. It seems like reasonable numbers. So now I would want to plot this to see how it looks, right? So the other thing that I mentioned earlier is you probably are going to be interested in economic limit. Otherwise, this decline is going to go on for a long, long time. So 150, since this is monthly data, roughly 30 days in a month, 150 divided by 30 is 3. So this is like saying my economic limit for this well is 3 barrels a day. Okay. So I create an empty data frame that starts at the highest, so the end of my X data. So this point starts here.
Eli, I just want to point out that's a stripper well and they dance.
Yeah, it definitely will be at the end of its life. I don't know what it's at now. 360 a month, so it's getting there. There's nothing wrong with stripper wells. Oh man. Okay, so where was it? Yeah, so I create a data frame. I want to take it out to the future because I'm looking for a value. What's this well going to deliver if I buy it? What sort of life does it have left in it? So 240 is adding 20 years arbitrarily. I could, 20 years is out of any time frame I care about. That's for sure. So for that data frame, now it's just an index of normalized month values. I add a QCalc column, which uses the DCA parameters that I fit previously to recalculate for all my new data, because I only matched till the end of this. I don't have any values for my future. So that's what I'm doing here. I'm passing this equation its own the variables that I fit previously. Okay, and then I say, now that I've created this, it goes out 20 years, but you know what? I don't care about anything below 3 barrels a day. So let's eliminate that. That's what I do here. And create a variable called PDP. That's Oilfield lingo for proved, developed, producing. So that's how you could classify.
That's Oilfield lingo for money.
For money, that's right. So if you're trying to buy a well, you'll hear PDP, and you'll ask what is the PDP, and that will tell you. It's really not best represented as a single number because time value of money is very important. So 10,000 barrels is amazing today. 10,000 barrels in 10 years from now has much less value in today's dollars. So that's what I mean by that. But just for giggles here, I create a variable. This is essentially telling you how much oil will this well produce in the future if you cut it off at 3 barrels a day. So I call this column. I say I only am interested in things greater than the end date, right? So greater than this is all I'm interested in because we don't want to put a value on the past, and sum it all up. Then I want to plot this stuff, so I create a figure. I plot our production data, which I already showed you how to do before. I'm just redoing that, and then I'm plotting my new DCA fit data, which includes the future, right? So now we get this, so we can see here in the future. So it ends set at 74 months, and you can tell that that rate, the next rate would have been below 150. So that's why it ends there. And we can see our variables. So the remaining production from that well is going to be 7,040 barrels according to this. It looks like a pretty good fit. So it looks like our optimization tool, the curve fit function from SciPy, did a good job. The other way you could have done this is manually type in guesses until it looks like it fits good, which is annoying. This is better for getting at least a good starting point. It's almost impossible to avoid manual interference in a DCA analysis, but this can at least get you to a starting point that's interesting and closely fitting your data. So, that really concludes the DCA fit part. The only part that I could think of after this would be to plot all of the data with the curve on it. So you can show this to your boss and say, this is the fit I got. This is the remaining oil that I see coming from the well. And you could even do like a NPV10 version of this. You could take this and do a bunch of stuff, like create an economic model that's in the form of a function that you pass this data to, and it creates a value based on your net revenue interest and your working interest and capital expenditures you're expecting, and so on and so forth. You could essentially build this out into your own PhD win, if you're familiar with that. So, that concludes that. I tagged on something here on the end. Just I was trying to learn something new, how to create an interactive Plotly chart where you can cycle through different wells with a drop-down menu. This could speed up your analysis by just cycling through each well, and you could have a dictionary for the B value, so you can manually change these declines. I tried to do it automatically, and it didn't do a great job because, like we know, there's these periods where there's different recompletions that you might need to isolate. So that's in the code. I've got all this stuff hosted on my GitHub, so the link should be shared with you. I also have an article that I turned this into a medium.com article because I write articles for analytics video when I feel like it. So feel free to fork this and check out the article and continue to watch HackerVillage, definitely, because I think there's going to be some even better presentations in the future.
Well, Matt, does that answer all your questions you had about DCA and all the stuff you were trying to learn as a geologist?
Yeah, me and Eli were actually chatting earlier today about this. I showed him a couple screenshots real quick of the tool that I built up. It's pretty close to that. I actually, I like the Plotly on there. I did mine with Matplotlib, and I used widgets, slider bars, so I could it did an automatic fit, and then I went in and then I could tweak it.
Yeah, so the Plotly, apparently I learned in doing that last bit of code that you saw there, it's actually pretty limited in its interactiveness, because I've done your method as well before, where I used widgets essentially, and it's more versatile. It's harder. It's a little more dense code to do the widgets, I would say. But you can do more. So Plotly is limited to one interactive, either drop down or slider.
Yeah.
Well, huge shout out. I mean, Eli, thank you so much.
Yeah,
I've been waiting
great
to get an engineer on HackerVillage and get away from all these crazy geos, No offense, Matt, or anyone listening. But this was awesome. Thank you so much for taking us from the very beginning
that was awesome.
to literally the very end, and then what you're building out in the future. For everyone watching, if you are not already following Eli on LinkedIn, you are doing yourself a disservice. So go and be friends with him, because he's always putting out articles, he's putting out new code, and he is literally building workflows from the beginning to the end for everyday tasks. So let's see. There's one. Oh,
yeah, I just posted the link to the article.
But I will be sure his GitHub and everything you've seen tonight is linked below in the show notes. And if everyone watching, please go on, hit subscribe on our YouTube, and leave us a rate and review on this HackerVillage episode, because the more information you leave us, the better we do, and the more people we can find like Eli to help pay it forward for open source, collaborative, hands-on coding. As always, another huge shout out to all our sponsors for making this possible. We understand that the oil industry is sort of in turmoil, so we want to make sure that there are no paywalls, nothing blocking your ability to add another tool to your tool belt and pay it forward. So, Eli, again, this was freaking killer, and I can't wait to get it up on the YouTube channel this week.
Yeah, sorry about the video.
I'll be sure to add your head in. Don't you worry.
I swear I'm good with technology.
Hey, Eli, Zane had a question.
Yeah, let's
unmuted us.
Did he?
Super cool talk, applause. Did you attempt to include completions or recompletion information in this analysis? Seems like it could be an interesting thing, maybe hard to qualify. Or quantify.
What do you mean by include?
If you would do that in a completion analysis more so than just DCA, what he showed you with the 3 potential declines is exactly how you would look at it. He's just calling it recompletions, but honestly, it could be an ESP down to a pump jack. It could be some sort of random workover where they had shut in for X amount of days and then they had a spike in IP. I mean, that could be just about anything. So
yeah, it's some sort of well event. So if you look at the details of ARP's equation, that you need a steady decline. So if there's any sort of event that disrupts the steady state flow of your well, then you want to grab that most recent.
You know, I guess you could go in and go through sundry reports.
Sundry.
Sorry, I'm a geologist. I look at rocks. But a sundry report, and you could go through those and do that and then look at the events but correlate it back. I mean, that'd be a lot of work.
So not all events are covered in sundry. You'll have to look state by state, but you are correct. That is a way to map it back. However, most of this will be occurring in terms of maybe an acquisition, so you have a due diligence period, you're pulling just raw data from, say, drilling info, or like Eli showed through the state. You would be doing a full DSU analysis if you went well event by well event, but that is something that happens.
Yeah, sometimes you don't have the luxury. So let's say that this field's up for bid and the bid's due at the end of this week and you have 380 wells. What are you going to do?
You're not going to call a geologist.
Are you going to try
Actually, you will call a geologist.
Yeah, so it's just, like I said, the real way, if you're spending millions of dollars, yes, I'd probably be opening sundries and trying to figure out exactly what is going on here. But, just showing an example workflow and how this stuff can be used to help you get the job done.
And to Zane's final comment, he is right. Those wells have been messed with for quite a bit because they are on some sort of water flood or CO2. So they're in secondary or tertiary recovery processes, which means that there has been some sort of workover completed. But we would have to, Eli's point and Matt's point, we would have to go to all the sun dries and understand exactly what's going on.
Yeah. So this is a CO2 flood by Denbury. If you want to know the details, so.
Well, heck, Matt, did I cover everything? Again, Eli, this is just killer. I can't wait to get this up and out and spread out to the oil and gas community. And if you are in wind, solar, geothermal, all production data is time series data. So exactly what Eli showed you can be applied to multiple industries, fringe industries on energy. I mean, just anywhere and everywhere. So all you have to do is take the idea and apply the technique.
Yeah, thanks for listening. I know there's people in Nigeria and Kazakhstan and the Middle East that have reached out to me and said they're listening. So I appreciate that and look forward to maybe another one in the future.
All right. Again, everyone hit subscribe, follow Eli on LinkedIn, and we will be back with you next month for a final 2020. Wait, it's only October. We have 2 more before the end of 2020. So stay tuned. Follow the Crude Audacity podcast on LinkedIn because that is where we make all of our announcements. And for shits and giggles, if all of you could go on to Apple and leave me a 5-star review there for the Crude Audacity, I'd appreciate it.
Thanks again, Eli. That was awesome.
Thanks so much, guys. Have a great night.
Appreciate it,
folks.
Bye.
Take care.